Welcome back to Chemistry from Jay's House. We're continuing our review, and today we're going to review two things. We're going to review chemical bonds and reaction rates. So we're going to talk about atoms sticking together and how quickly or slowly are they willing to change who they're stuck to. So that's the two concepts today. And it all kind of comes back to the periodic table. So to truly understand chemical bonds, to truly understand how stuff sticks together, we need to know what atoms want. And what they want is they want to be right here. This right here is group 18, has 8 valence electrons. Its s orbitals and its p orbitals are filled, and that's the winner. And that means that these guys right here in group 17, which have 7 valence electrons, are just one away. These guys are so close. Oh, if you're in this row right there, you are 1 electron away from winning the game. Because this row right here, this guy right there with 8 valence electrons, that row right there, those guys are winners. All right? And so this row right here just wants to get 1 more valence electron to win. This row right here needs 2 more valence electrons to win. This row right here needs 1, 2, 3. As you might guess, these guys are super hopeful because they only need 1 more. These guys, somewhat hopeful because they just need 2 more. Once you get out here where you need 3 more valence electrons, they're not super hopeful. But what if, I don't know, let's say this guy gets 2 valence electrons. Well, 1 would go right here, and then the second one would force it back over here. You've gone too far. And these guys, what you'd like now is actually to get rid of a valence electron and loop back to here. So these guys here are trying to get valence electrons to add up to 8, where these guys here are trying to get rid of valence electrons to loop back here. So again, these guys are trying to gain electrons to win, and these guys are trying to lose electrons to zip back around, loop around, and win. So let's leave the periodic table out over there for now and talk about this. Okay, well, the easiest thing is sharing is caring. So if we take non-metals, anything up in here, these guys are so close to winning the game, so close to being there, that they are not going to give up their valence electrons. So let's say we have, I don't know, we'll say fluorine, which is right there, and chlorine, which is right there. And they both have 7 valence electrons. So I'm just going to do a quick Lewis dot diagram. There's 2 in its s orbital. There's 1 in its px, 1 in its py, 1 in its pz, 2 in its px, 2 in its py, and there's a huge missing gap right here, right? If it could just get an electron right there, it would be super happy. But tragically, it can't. Now, chlorine, which is right under it, has the same thing. It has 2 in its 3s orbitals, 1 in its 3px, 1, 3py, 1, 3pz, 2, 3px, 2, 3py. And it has that same gap right there, and it's pz, but it's 3pz. Now, chlorine asks fluorine and says, hey, can I have one of your valence electrons? And fluorine goes, oh, you must be kidding me. I would never give you a valence electron because that would make me further from winning. I only need 1 more valence electron. Look right here. If I can find 1 more valence electron, I would win the game. Chlorine goes, yeah, same for me. So what do? Stalemate. I'm not going to give you a valence electron. I'm not going to give you a valence electron. Wait a second. What if we shared a valence electron? What if I took one of my valence electrons and gave it to you part-time, and you took one of your valence electrons and gave it to me part-time, and that we each have 1 valence electron that can go to either atom? So like these electrons here, those will only orbit me. But this guy will have a travel visa to you. So it can orbit me and it can orbit you. Oh, and you're saying that, so all these other electrons would only orbit me, but this guy right here, I would give him a travel visa to you, and he could orbit me or he could orbit you. Exactly. Then occasionally, that valence electron would be here. And occasionally, chlorine would be happy. And occasionally, it would be back. And, they're, back to where they started. And occasionally, that valence electron would be here. And fluorine would be happy. And occasionally, it would actually be all kinds of flipped around. Ah! But the key is that occasionally there will be moments where if they share valence electrons, one of the atoms will have all 8. And that's totally worth it to atoms. Even though this guy now only has 6. He's actually gotten further from winning. But if he waits long enough, one of these will come back over here, and this guy will come home occasionally, and he will occasionally win and have all 8. So that's what happens. This is called a covalent bond. A covalent bond is when atoms agree to each let one of their electrons go to another atom periodically. So occasionally they'll just be like this, and occasionally they'll both be here, and occasionally they'll both be there, and occasionally they'll be switched. And so occasionally one will be happy and one will be bummed. Occasionally they'll each be back to having 7, and occasionally the other will be happy and this guy will be bummed. That's a covalent bond. Now, if we are going to draw a covalent bond, we would do a Lewis dot diagrams of each. And then I find the easiest way to do it is just take this guy and put a nice little circle around there. And then when we count, we say it has 1, 2, 3, 4, 5, 6, 7, 8. It has access to 8 valence electrons. And this guy has access to 1, 2, 3, 4, 5, 6, 7, 8. Has access to 8 valence electrons, but it's not full-time access. They are sharing. Co means to share, so covalent bond means they are sharing valence electrons. That is a covalent bond. What you'll see often is, instead of loops, what you'll see often is just a bar. And the bar means 2 valence electrons, 1 given by each atom. So again, doing the count, it would be 1, 2, 3, 4, 5, 6, 7, 8. And the same thing for fluorine. That is a covalent bond. So one bond is covalent bond. Equals sharing. Aww. Okay. Well, what if we, take chlorine again with its 7 valence electrons, 2 in S, 2 in PX, 2 in PY, 1 in PZ. Still has this huge gap right here that I'd like to fill. And now we put some sodium in there. Well, sodium has 2 choices to be happy. One way it could be happy is it could add 7 more valence electrons. That sounds like a lot of work. Or it can take the shortcut, and that is hidden behind this valence electron. This valence electron leaves on an earlier energy level. There's actually 8 valence electrons waiting in the wings. Now, unfortunately, they're at an earlier energy level, a lower energy level. So really, sodium only has 1 valence electron. And we know that because it's in the first group of the periodic table. But if we could just get rid of it, then these 8 valence electrons that are in, or these electrons that are in an earlier, lower energy level would then become valence electrons. They'd be on the outermost energy level. So what happens here? Not a covalent bond. We don't want no sharing. Sodium wants to give its valence electron to chlorine. So that's exactly what it does. And now, though we write it with no dots or X's, and I've just put little dots here to remind us that there's 8 in the back, we actually would write it as completely empty. Sodium has 8 valence electrons from a lower energy level. Chlorine has 8 valence electrons, and this is full time. Chlorine, it's not part time 8. It has 8 all the time. Sodium has actually given up completely its valence electrons. So ding. This has full time 8. This has full time 8. Everybody's happy, but there is a price, and the price is magnetism. Now, if there's no such thing as magnetism, chlorine would just leave. See ya. Sodium would just leave, and they'd never talk to each other again, and it'd be great. But tragically, chlorine has picked up a charged electron. It has a -1 charge. Now, if the number is 1, we don't write it. So we just put a negative sign. But there's a ghosted 1 here. There's a 1 that's implied there. Right? And sodium just lost a valence electron, just lost an electron, which means it now has 1 more proton than electron. So it has a positive charge. So these guys actually they don't need each other. They would love to run away, but magnets. Magnetism sticks them together. This guy has a -1 charge. This guy has a +1 charge. And now, click, they're stuck together. Even though they're both individually happy, they can't get away from each other just because of magnets. Bummer. And that, right there, is called an ionic bond. An ion is anything with a charge, and the whole reason these guys stick together is charges, negative and positive charges. So the second type of bond is an ionic bond, which is stealing and magnets. By taking a valence electron, this got a charge, this got a charge, it became magnetized. Back before theft happened, there were no charges. So when this guy, that valence electron, was still part of sodium, and chlorine's only had its 7 valence electrons, there were no charges. So not only is there stealing, there's also the addition of ions. They become ions, and that's why it's called an ionic bond. Okay, so I get it. If 2 nonmetals who are so close to winning the game get together, their only option is sharing. So if both atoms are nonmetals, you're going to get a covalent bond. If one is a metal and one is a nonmetal, then the metal will give up its valence electron. The nonmetal will take it, so we'll have some stealing, but they'll become magnets and they'll stick to each other. But what about 2 metals? I mean, what about that? Now, to truly understand that, you have to know a little bit about how metals work. So let's say that we are going to take some iron and we're going to try to put some, I don't know,